Now, the quotient rule. Now, the quotient rule should actually kind of make sense. All it's really saying is, and I'll give you an extremely simplified version of this really quickly. Let's say we had x to the third power over x to the second power. Well, that means we have x times x times x over x times x, right? Now, if you have a like factor in the numerator and the denominator, you can cancel them out. So we'd say 2 of these on the top cancel with 2 of these on the bottom, leaving me just 1 in the top, which just leaves me x to the first, right? But we could kind of just use these exponents to do the same kind of cancellation, right? 3 on top, 2 on the bottom, 2 on the bottom, right here, right? We'll cancel out with 2 on the top, just like this, leaving me just 1 left on the top, which we see visually right there, right? So we end up with 2 to the first power. Okay, now, then rather than expanding out and rewriting it without the exponent, and then doing the cancellation individually, we can just use the exponent kind of as a shorthand for the same kind of operation. So in this case, we had 8 5s on top. We have 6 5s on the bottom. So these 6 on the bottom are going to cancel with 6 of the 8 on the top, leaving you simply 2, right? 8 minus 6 is 2. So I'm actually going to write out the step. You don't have to do this. But I'm actually going to write the 8 minus 6, and that gives me 5 to the second power, right? All right, let's try the next one. Now, you might find this a little confusing, but it really shouldn't be. So let's just kind of flip the paradigm a little bit. Let's say we have, I don't know, 2 to the second over 2 to the fourth. Okay, like kind of like just like the previous example, but now you have more in the denominator than the numerator. In this case, you could simply say, well, it's 2 times 2 over 2 times 2 times 2 times 2, in which case the 2 2's on the top cancel out with the 2 2's in the bottom, leaving me how many? 2 2's on the bottom, right? Which we would simply write 1 over 2 to the second power, which is, of course, is just 1 over 4. Now, the reason I kind of wanted to go over that is because when things cancel out, they don't just disappear. Technically, these go to 1. So this goes to 1, and that goes to a 1, right? So when things, so for instance, 2 divided by 2 is 1, right? So technically this would be 2 divided by 2 is 1, 2 divided by 2 is 1, 1 times 1 is 1. Yeah, okay. And right here it would be 2 divided by 2 is 1, 2 divided by 2 is 1, and 1 times 1 is 1, and 1 times 2 is 2. But since normally you multiply the 1 by other things, you don't actually write this step. There's no reason to. So again, the whole gist of this is you need to make sure you leave this 1 in the numerator. Don't put just the answer is 4. It's 1. Again, you have to remember to keep that over 4. Okay, so let's actually try to think about this. So there's a couple of ways to do this. One, you can do it the long way using this equation, and sometimes you have to, especially when things get more complicated. So I'll do it the long way first, and then I'll show you the shortcut. So for instance, let's say we say 4, and the numerator's exponent is 2. The denominator exponent is 9, so we're saying 2 minus 9, and that gives me 4. 2 minus 9 is a negative 7, and that's understood to be over a 1. And then to get rid of this negative 7 exponents, we want to put it on the bottom. So we would simply say that's 1, right? And again, because even though we move this 4 to the negative 7th power, there's still an understood or implied 1 up there. So we have to leave the 1. So we put it on the bottom, and then 1 times 4, right? 1 times anything is going to be 4, in this case, to the 7. Okay? Now, that's such a large number, 4 to the 7th. They probably don't want you to simplify that because that's like 2 to the 14th power. It's going to be like over 16,000. So that's a ridiculous number. So oftentimes, whenever the numbers get really large like this, my math lab will actually accept it in exponential form. It will actually say so underneath where you enter the problem, what form it wants it in ideally. And so that's, well, it's beyond a hint. Now, sometimes it's kind of ambiguous. You can try it either way. But again, whenever the numbers get into like the tens of thousands or even thousands, oftentimes they're going to want you to just leave it in the exponential form. So just be careful, read your where you enter the answer to make sure that you enter it in the correct form so you get full credit. Okay, now there's a couple of ways to do this one. Now it might occur to you that because both of these have negative exponents, I could simply switch positions, right? I'll put that 5 to the negative 3rd power on the bottom, 5 to the negative 7th power on the top. And that's true. You could do that. Or we could just do the rule as it stands, right, without any of that extra step, right? In which case we would simply say negative 3 minus negative 7, which is equal to 5 to the negative 3 But if you subtract a negative, that's the same as adding, which would be like adding a 7, in which case you'd say negative 3 plus 7 is simply 4, 5 to the 4th power, right? So that'd be 5 times 5 is 25, times 5 is 125, times 5 is 625. So you get 625, and then of course you're done with that. That's it. Now, if you would have switched the positions of the negative exponents, and I know sometimes it's confusing that you can do these multiple ways, but I just wanted to point out that just because it occurred to you to do this problem differently than how I did it over there, it doesn't mean you're wrong. As long as you're using the exponent rules correctly, you will eventually get the correct simplified answer. Okay? So what we would do is, at this point, you could simply say, oh, 3 of those will cancel out with 3 of those, leaving me 4 on the top, which is kind of a mental shortcut. Not a bad idea to do it that way. But if you write it out, it'd be 7 minus 3 equals 4. And of course, you still end up with the same 625. So not too bad, right? Now, this one looks a little bit different. It's the same kind of concept, but now, of course, we're dealing with variables. Okay. Now, again, you have a couple options here. One, I could push this to the top, and I could use the exponent product rule, right? Or I can actually just use the quotient and just deal with the negative. And they're both correct. There's nothing wrong with either one of those. So the numerator's exponent is 5. The denominator's exponent is a negative 3. So 5 minus negative 3. Subtracting a negative 3 allows you to add. So we would say Q5 plus 3, which is Q to the 8th power. Now what would happen if I would have just switched positions? I would have ended up with Q to the 5th times Q to the 3rd, both in the numerator. The denominator would have been over 1 and then it just would disappear, right? But now because they're both in the numerator, instead we're multiplying these together, in which case we would use the product rule. So we would say Q to the 5 plus 3, which gives me Q to the 8th, right? Okay, let's go down just a little bit more. All right, so we're going to move down to a few more problems. Okay, now in this case, we don't have any negative exponents to deal with. Usually, if you have negative exponents, you probably want to deal with those first, and then you probably want to use the quotient rule. Now, I want to use this, I want to do shortcuts on this one just to show you how easy this is once you get the shortcut. 2 of the 3's on top cancel out with 2 of the 3's on the bottom, but since there are more 3's on the bottom, the leftovers have to end up on the bottom. So you just end up with 3 to the 2nd power on the bottom. Now in the x's case, you have 5 x's on the top, you have 3 x's on the bottom. 3 of these will cancel out with 3 of those, leaving you the leftovers on top because there are more on top. So you end up with x to 5 minus 3, right, which is 2. Okay, now in this case, you probably really need to simplify the 3 to the 2nd power. It's not that big of a number, so they're probably going to want you to simplify that. So we're just going to leave that at x squared over 9. Okay, here we go. Now in this case, a couple of ways you can do this. Again, you could just use the quotient rule as it stands, in which case you're simply going to say negative 2 minus negative 4, and that would give you negative 2 minus negative 4 is the same as negative 2 plus 4, which gives you a 2. And that's a perfectly acceptable answer. I mean, technically, you could expand this. There's a pattern for this, or you could rewrite it without the exponent and do foiling, distribute it. But this is a perfectly acceptable answer most of the time, so I wouldn't worry too much about it. Now, in this case right here, we have to move things around. Now, you could use the quotient rule right off the bat. That's a possibility. Or you could move everything with the negative exponent as a first step. Now, again, as a rule of thumb, I like to get rid of the negative exponents because it's so easy to make a sign error, and this sometimes helps you avoid that. So, but it's not wrong if you want to keep them a little bit longer. So I'm going to put that on the bottom. Right, I'm going to rewrite everything. I keep the 7. That didn't go anywhere. Y to the 2nd. That didn't go anywhere. We also have a 2, right, times a 2. So instead of a negative first power, because it was on the bottom, now it's on the top, so it's a positive first power. We have a y, but instead of it being to the negative 5th power when it was on the bottom, now it's a positive 5th power. All right, so now we moved everything. All right, so let's see what's on the bottom. Now, the x squared stayed on the bottom, but now we have the addition of x to the negative 3rd, which was on top. We put it on the bottom, and now we multiply it, x to the, not negative 3rd, but positive 3rd, right? Switches signs. Okay. Now, whatever's left over, we're going to multiply it together, and if they're the same factor, we're going to use the product rule. to add the exponents, right? So in this case, we're going to keep the 7. We're going to keep the 2. Now you could just multiply 7 times 2 and get 14, obviously, at this point. I'm going to hold off a little bit on that. Then we'll say y to the 2nd times y to the 5th, and we're going to use the product rule. So we say 2 plus 5, right? Now 7 times 2 is 14, and y to the 2nd times y to the 5th, 2 plus 5 is 7. So we use the product rule in that one. Now on the bottom, we have x to the 2nd times x to the 3rd. Again, we're going to use the product rule, x to the 2nd, and then we're going to say plus the 3rd, right? Product rule, and that one that gives me x to the 5th. Just like that, right? Okay. Now let's scroll down a little bit. Now these are just calculator problems. You really just need to learn how to use your calculator. If I was there, I could actually show you how to use different kinds of calculators, but you do definitely need to learn how to use your calculator. And these are just trying to figure out what different graphs look like, right? So we have 4 to the x power. You could just plug in numbers, and that'll give you a few coordinates, and then you plot those points, and then you kind of draw a curve through it. Same thing on this one. This is just kind of a plug-and-play problem. But just to give you an indication of what these would actually look like, the first one, 4 to the x power, right? 4 to the x power would look like this red line right here, and it crosses at 0. It crosses right there at 1, right? So these are half grids. Now the other one, on the other hand, is the blue one, and it flips, right? But again, it still crosses at 0, x value, y value 1, and that's not an accident, right? Because anything to the 0th power is 1. Now the one with the base that's larger than 1, when you take it to a power, is going to increase exponentially. The one with the base that is lower than 1 is going to decrease, right? And then if you have negatives, it's actually going to shoot up to infinity. And that's it for 4.1. All right.